Okay. Now, initially, I will define the primary function of cardiovascular system. Let's look at that. Let me adjust the other things. Okay, no. Yes, the primary function of the cardiovascular system is to deliver blood to tissues, and this provides us some essential. This provides some essential nutrients to the cells for metabolism and removes waste products from the cells. So, the heart serves as a pump, which by contracting generates the pressure to drive blood through a series of blood vessels. Yes, in the first part of this course, I will tell you some anatomical details which are necessary for us. The vessels that carry blood from the heart to the tissues are the arteries. And then, you see the figure there on the right side. And then these are the under high pressure and contain a relatively small percentage of blood volume. And the veins they carry blood from the tissues back to the heart, are under low pressure, largest percentage of blood volume. So within the tissues, thin-walled blood vessels called capillaries, and then they are interposed between the arteries and the veins, and the exchange of nutrients, gases, and fluid across the capillary walls. So the cardiovascular system involves also several hemostatic functions. It participates in the regulation of arterial blood pressure. It delivers regulatory hormones from the endocrine glands to their sites of action in target tissues. It participates in the regulation of blood temperature, another important part. And then it is involved in the hemostatic adjustment to altered physiologic states, such as hemorrhage, exercise, of course, and then the change in the posture. So distribution of blood in different parts of the circulatory system, you can see on the right figure. Look at that, please. Its distribution for pulmonary circulation is 9%, and then for the heart 7%, and then arteries 13, and the arterioles and the arteriolites and the capillaries is 7%, and then in the systematic circulation, big amount of it, as you see, 84%. Venous and venous sinuses is about 64%. These are the distribution of blood in different parts of the circulatory system. So the places are changing according, as you see here, and then the left and right sides of the heart and the blood vessels are shown in relation to each other. Each side of the heart has two chambers, an atrium and a ventricle, connected by one-way valves called atrioventricular valves, so AV. AV valves are designed to blood can flow only in one direction from the atrium to the ventricle. The right ventricle pumps blood to the lungs. The left heart and the right heart function as series so that blood is pumped sequentially from the left heart to the systematic circulation, to the right heart, to the pulmonary circulation, and then back to the left heart. This is the pathway. So the left heart and the right heart have different functions. The left heart and the systematic arteries, capillaries, and the veins are collectively called systemic circulation. Yes, systemic circulation. The left ventricle pumps blood to all organs of the body except the lungs. And the right heart and the pulmonary arteries, capillaries, and veins are collectively called the pulmonary circulation. So let's look at here. So we have a figure. We have left and right sides of the heart. This is actually the schematic diagram showing us the circuitry of cardiovascular system. And the arrows show the direction of blood flow. So let's look at the details here. This is the schematic diagram, as I said. Left and right sides of the heart and the blood vessels are shown in relation to each other. As you see, each side of heart has two chambers, atrium, ventricle. They are connected by one-way valves called AV valves. The AV valves are designed so that blood can flow in one direction. We said that. The left heart and the right heart have their own function. We also said that. So another thing I will define here, cardiac output. Okay, cardiac output I will define. The rate at which blood is pumped from either ventricle is called the cardiac output? Because two sides of the heart operate in series connection. So side by side, you can think side by side. So because the two sides of the heart operate in series, the cardiac output of left ventricle equal to the cardiac output of right ventricle in steady state. In steady state. The rate at which blood is returned to the atria from the veins is called venous return. Again, because the left heart and the right heart operate in series, venous return to the left heart equals venous return to the right heart in steady state. Finally, we can say that in steady state, cardiac output from the heart equals venous return to the heart. We have also blood vessels here. The blood vessels have some functions. They serve as a closed system, passive conduits, delivering blood to and from the tissues where the nutrients and wastes are exchanged. The blood vessels also participate actively in the regulation of blood flow to the organs. When resistance of blood vessels, particularly of arterioles, is altered, blood flow to that organ is altered. We will talk about this resistance, by the way. I will define for you this resistance. So, and what is the relation with this resistance and the blood flow? So the rate at which blood is pumped either ventricle is called cardiac output. We said that because two sides of the heart operate in series, the cardiac output left ventricle equals the cardiac output right ventricle in steady state. We told about that. In this figure, there is a formula for the cardiac output. It's related with heart rate and the stroke volume. So stroke volume is about the blood volume and the vascular resistance, which we will talk about in our following slides, as I said. So I added here a simple example. If Jenny's heart rate is 60 beats per minute and a stroke volume is about 70 milliliter, what is her cardiac output? So we can calculate it from the stroke volume and heart rate, the cardiac output by multiplying this. As you see, it's 4,200 milliliter per minute. So the blood vessels functions, they serve a closed system of passive conduits delivering blood to and from the tissues where the nutrients and wastes are exchanged. So they are responsible regulation of blood flow to the organs. When the resistance of blood flow, particularly of the arterioles, is altered, blood flow, that organ is also altered. I repeat this part again for you. I will tell you the resistance details in our following slides, as I said. So let's look at this circuitry again. We have a circuit, we have parallel connection, series connection between the right heart, left heart. As you see, we can think in our circulatory system, we can think the organs parallelly connected to each other. So let's look at these details. We have a pathway here showing the blood flow by using some numbers. For one blood flow, look at the right side, we have one. So one oxygenated blood fills the left ventricle. Blood that has oxygenated in the lungs returns to the left atrium via what? Via pulmonary vein. This blood then flows from the left atrium to the left ventricle through mitral valve. So blood is ejected from the left ventricle in the aorta, and blood leaves the left ventricle through the aortic valve, which is located between the left ventricle and the aorta. As you see, when the left ventricle contracts, the pressure in the ventricle increases. This will cause what? This will cause aortic valve to open, and blood is ejected forcefully into the aorta. Okay, so this is actually the volume of blood ejected from the left ventricle per unit time. This is what? This is cardiac output. Blood then flows through the arterial system, driven by the pressure created by the contraction. Okay, let's look at third part. Look at 3 here. So as you see, after 3, there is a separation. There's a distribution. The total cardiac output of left heart is distributed among the organ systems via sets of parallel arteries. So we have parallelly connected, not side by side, parallel connected arteries. Thus, we can say simultaneously, approximately 15% of cardiac output is delivered to brain via the cerebral arteries. So 5% is delivered to the heart via coronary arteries, and 25% is delivered to the kidneys via renal arteries, and so forth. You can see the distribution there. So in this parallel arrangement of the organ system, it follows that the systematic blood flow must equal to what? Cardiac output. Again, please capture this point. Yes, 1, 2, 3, I said. So I added some details, please read you. So cardiac output is distributed various organs. I said that. I'm now at fourth part. So in the fourth, look at that, please. The bloods live in the organs in venous blood and contains waste product now. Waste product from the metabolism, such as carbon dioxide. The mixed venous blood is collected in veins of increasing size and finally in the largest vein. What is this vein? It is vena cava. Vena cava carries blood to the right heart. So look at 5 now. We are at 5 step. Because the pressure in the vena cava is higher than the right atrium, the right atrium fills with blood. And this is what? This is venous return. So in steady state, the venous return to the right atrium equals cardiac output from the ventricle. And then the mixed venous blood fills the right ventricle. Mixed, here actually, to the right ventricle through what? Through AV valve in the right heart called actually tricuspid valve. So look at that. It is at the 6th step. And the 7th, 7th, and 8th steps here, blood is ejected from the right ventricle in the pulmonary artery. And at 8, the blood from the lungs is returned to the heart via pulmonary vein. You can read the other details later here. So now I will tell you the details about the hemodynamic, which is more important for this course in addition of the anatomical details. So the term hemodynamics refers to the principles that govern blood flow in the cardiovascular system. So 3 basic principles are the same as those applied movement of fluids in general. Yes, we will think about the movement of fluids. So flow, pressure, resistance, capacitance are applied to the blood flow and from the heart and within the blood vessels. You can see these basics of circulatory physiology, Laplace law, Ohm's law, Poiseuille law, and Bernoulli's principle. These are our basic laws or principles we will talk about for this course. Now, let me check my slides. Yes. I hope we can finish. So types and characteristics of blood vessels. Initially, simply I will define for you. Blood vessels are conduits through which blood is carried from the heart to the tissues and from the tissues back to the heart. So in addition, some blood vessels, these are capillaries, are so thin-walled that substances can exchange across them. So look at that, please. We have a schematic representation of vascular bed. The direction of blood flow through the vascular bed is from artery to the arteriole, to capillaries, to venule and vein. So let me take the attendance again. So the amount of the students decreased. Okay, let's go on the types and characteristics of blood vessels now. Look at that, please. You can see here the area and volume contained in the systematic blood vessels. Look at aorta, look at arteries, look at capillaries. So the purple part shows you the area and the brown part shows you the blood volume in this graph. So the blood vessels are described by the number of each type, the total cross-sectional area, and the percentage of blood volume contained. So look at that, please. Capillaries, area is higher, all of them. After that, veins are coming. And if you look at the blood volume, the veins and arteries takes the big part. Now let's look at the cross-sectional area of them. Aorta, small arteries, capillaries. Look at that. Capillaries cross-sectional area is really high. After that, veins are coming, and the aorta cross-sectional area it is about 2.5 centimeter square. Now, if we talk about the diameter of them and some specific tissues these vessels contain, look at that, please. So, artery mean diameter is 4 millimeter. You know, milli is 10 to the power of -3. Look at the arteriole, look at the capillary, look at the venule. If you see them, if we look at these numbers, you will see that the micrometer, 30 micrometer for arteriole, for capillaries is 8 micrometer. Micro is mute your microphones.
Thank you.
So if you look at the tissues, endothelium tissues, smooth muscle tissues, arteries contain the highest amount of smooth muscle. And if you look at the capillaries, there is no smooth muscle, there is no fibrous tissue, there is no elastic tissue. They only have the endothelium tissues. Look at them. For the veins, they contain smooth muscle, fibrous tissue, elastic tissue, and endothelium. These are the diameter differences, and then the tissue separation of these vessels. Yes, if you look at these, the thickness of the arterial wall is a significant feature, actually. The arteries receive blood directly from the heart and are under the highest pressure vasculature. So arterioles are the smallest branch of the arteries, and their walls have extensive development of smooth muscle, and they are at the site of highest resistance to blood flow. Okay, so you can read also the other anatomical details here. So the capillaries are thin-walled structure, lined with a single layer endothelial cell, which is surrounded by a basal lamina, and some other anatomical details. Lipid-soluble substances. You know the solubility details of oxygen and carbon dioxide. Lipid-soluble substances cross the capillary wall by dissolving in and diffusion across the endothelial cell membrane. In contrast, we can say water-soluble substances cross capillary wall either through the water-filled spaces between the endothelial cell or through a large pores in the walls in some capillaries. So in this figure, you can see the blood vessel types and their functions. So how their tissues are differ, and you can see their functions in the circulatory system. These are again some anatomical details you can read. So the velocity of blood flow is the rate of displacement of blood per unit time. Velocity. So rate of displacement of blood at a per unit time. Displacement divided by unit time. The blood vessels of the cardiovascular system vary in terms of the diameter and the cross-sectional area. And these differences in diameter and area in turn actually have profound effects on velocity of flow. So diameter is effective on velocity, okay? So the relationship between velocity and flow and the cross-sectional area depends on vessel radius or diameter. 2 times radius will give us diameter. So velocity of blood flow is V here. So its unit can be say as centimeter per square, and Q is flow, which is milliliter per square, and the cross-sectional area for the vessels can be defined as centimeter square. So the relation between these, as you see, velocity is equal to flow divided by the cross-sectional area. So velocity of blood flow is linear velocity and refers the rate of displacement blood per unit time, and flow is the volume of flow per unit time. Volume of the flow, a specific volume of the flow in unit time, and it's expressed in unit of volume per unit time. So area, you know what's area? It's cross-sectional area of the blood vessel. So look at the figure, please. So area is different, flow is same. And how the velocity is affected? So velocity is decreases according to what? According to increase in amount of the area. This is one important biophysical reality. As you see, the flow through each blood vessel is identical at 10 milliliter per second. And because of the inverse relationship between velocity and cross-sectional area, when the vessel diameter increases, the velocity of flow will decreases. Now, I added here another example. Let's say that a man, it is a measured value, a man has a cardiac output 5.5 liter per minute, and the diameter of his aorta is estimated around 20 millimeter. The total cross-sectional area of his systematic capillaries is estimated to be 2,500 centimeters square. What is the velocity of blood flow in the aorta relative to velocity of blood flow in capillaries? A simple example I added here. And you can see the calculation. So according to cardiac output, and by dividing the cross-sectional area for the capillaries and the aorta, first part on the right figure, blue area, look at that, please. First calculation for the capillaries and the second calculation for the aorta, and how they differ, how the values changing, you can see in the figure. This is a simple calculation area. So let's calculate the area here. Maybe we can think that it's about what? It's about the diameter. So diameter is 20, radius is 10. So as you know, area can be calculated as pi r square. So pi r square is the multiplication of the pi with the radius square. So it's which is a constant value 3.14, and then 10 millimeter is actually 1 centimeter, and we can calculate the cross-sectional area here. So we can say velocity in aorta is around 800-fold that in the capillaries. So we can say this calculation confirmed the previous discussion concerned velocity of blood flow. Okay, let's look at now other details. Blood flow through a blood vessel or a series of blood vessels is determined by two factors. So pressure difference between two ends of vessel and the resistance of vessel blood flow. So pressure difference, resistance. Pressure difference is driving force for blood flow, and the resistance is an impediment to flow. Please remember Ohm's law. So in Ohm's law, we have a formula like that. Potential difference is equal to current times the resistance. So we can say here in the blood for the blood flow pressure and resistance is the analogous of to the relationship of current, voltage, and resistance in electrical circuits. So we can say here blood flow is similar to current flow. The pressure difference is driving force is analogous to the voltage difference. So flow is possible if there is a voltage difference. So you can say pressure difference is driving force here, and hydrodynamic resistance is analogous to the electrical resistance. So the equation for blood flows is expressed like that. So flow is equal to pressure difference divided by resistance. Okay, so this is the relationship between flow, pressure, and the resistance. This is the second definition for it. So the magnitude of blood flow, which is Q, is directly proportional to the size of pressure difference, delta P, or the pressure gradient. Pressure difference, pressure gradient. Gradient means difference. You can think like that. The direction of blood flow is determined by the direction of pressure gradient, and it's always from the high pressure to the low pressure. Don't forget that. It's always like that. So another example, blood flows from the vena cava to the right atrium because the pressure in vena cava is slightly higher than the right atrium. So blood flow is inversely proportional to the resistance if you think the formula again. The increase in resistance, for example, by the arteriolar vasoconstriction, this can be a reason. This will decrease the flow. Decrease in resistance will increase the flow. So the mechanism here for changing blood in the cardiovascular system by changing the resistance of blood flow, particularly arterioles. So another definition now I will make for you. Total peripheral resistance. So this is the resistance of entire systematic vasculature is called the total peripheral resistance or systematic vascular resistance. So total peripheral resistance can be measured by substitution cardiac output flow. So you know what is cardiac output for flow. And the difference in pressure between the aorta and the vena cava for pressure gradient, pressure difference, which is delta P. So resistance in a single organ, we can also think about that. The flow, pressure, and the resistance relationship can be applied on smaller scale to determine resistance in single organ. Yes, I added an example here. Please read. Please try to solve on your own. So resistance and blood flow, the blood vessels and the blood itself constitute resistance to blood flow. Relationship between resistance and the blood vessel diameter and the blood viscosity is defined by Poiseuille equation. Now we have another definition, blood viscosity. Yes, blood has a viscosity value. You can think the viscosity. Resistance to flow. For example, how can I explain? Think a cream and think water. A cream viscosity is higher than the water. So resistance to flow of a cream, when you try to pour it, for example, resistance of a cream to flow higher than resistance to water. If you think to flow, resistance to flow of a water, if you compare cream has higher viscosity if you compare with the water. So blood has its own viscosity, and this is defined by the Poiseuille equation. Now, the total resistance offered by a set of blood vessels also depends on whether the vessels are arranged in series. They have side-by-side series connection. They have also parallel connection. So they also depends whether the vessels are arranged in series or in parallel. So blood flow is distributed simultaneously among parallel vessels. Look at that, please. So it's their resistance changes, and according to their series and parallel connection, total resistance is also changing. Now, resistance to blood flow. Now let's look at details of Poiseuille equation. The factors that determine the resistance of blood vessel to blood flow is expressed by this equation. So R is resistance. So here we have nu, which is viscosity of blood. I said that for cream and water is different. Blood has its own viscosity. So L is length of blood vessel. So what about R? R is radius of blood vessel raised to fourth power of it. So look at the formula. A, 8 times viscosity of blood, length of the blood vessel divided by pi R4, or pi times fourth power of R. So these are the other details of the formula, step by step. If we give an example, if the radius of blood vessels decreases by 1/2, the resistance does not simply increase twofold. As you see, it increases 16-fold. So according to that, we can say a peripheral artery 1 is found to have 50% shorter than artery 2 compared to artery by factor has the flow of blood being increased. So we can assume that according to MRI results shows 75% of occlusion of the artery, and the clinical investigation shows that viscosity is decreased by 4-fold. So how resistance against flow would change? Think that, please. So maybe you can find the answer in this example. Please read this example again. I added here a calculation example. Please read it. So what would the flow be if the resistance were to increase 254-fold? Please look at the calculation details again and the factors. So at last, I want to tell you the series and parallel connection. So we said that it's important, it's affect the total resistance. So the resistance in the cardiovascular system, as in electrical circuits, can be arranged in series and parallel, we know that. So according to this, the total resistance will change. In series connection, total resistance of the system arranged in series is equal to sum of the individual resistances. So as you look at, we will sum all of these. For the parallel one, parallel resistance in a parallel arrangement is less than any of individual resistance. So this basic difference is so important. The total resistance in parallel arrangement of vessels in the cardiovascular system is less than any of individual resistance. So look at that, please. For the system, for the circulatory system components, how according to parallel and series connection, how it changes. Yes, another figure I added here, an example added here. Please try to solve it. I will also share the answers of this question I added here. For example, if you try to calculate total resistance here, how you can do that? As you see, R11 and R12 parallelly connected, and here these series they have series connection to R1, and again R21 and R22 parallelly connected, and they are in series with R2. So the total connection, the total part at the upper and lower sides of the figure has parallel connection. I will share with you the solution, but try to solve it. Another example I added here. Please again try to solve it. Yes, I want to tell you the details. I will finish at 41. Sorry, I will take the attendance. Okay, I take the attendance. I think the course will finish in a few seconds. At the other course, see you, okay? A student, right? Yep, see you. Your Wi-Fi connection has some problems. Okay. There is nothing to do. They told me take the attendance. Okay, let's go on now. Yes, I adjust my screen. I download the attendance list. At the end of the course, again, I will record the attendance list. Okay, now. We will describe the mechanism about the exchange of gases. We will discuss the importance of sufficient ventilation, perfusion, and how our body adapts when they are insufficient. We will talk about this today. Initially, I want to start the effect of pressure, effect of temperature, how they affect the solubility of gases. The solubility of a gas in liquid increases with an increase in pressure at given temperature. Initially, I can say that. So solubility increase with increase in pressure. So we can say conversely, the solubility of a gas decreases with a decrease in pressure and an increase in temperature decreases the solubility of a gas in liquids. As a summary, we can say like that. So also, we can talk about that. The pressure affects the solubility of a gas in a liquid much more than does the temperature. William Henry found that the solubility of a gas increasing with increased pressure. Sorry? Okay, so the Henry's law, please mute your microphones. A mathematical statement, a formula can be described by the Henry. Look at that, please. We have a formula, C equals Q times pressure of the gas. So in this equation, C represents the solubility of a gas in a particular solvent at a fixed temperature. So solubility can change, right? So P, you know that P is pressure, partial pressure of the gas above the solution, and Q is proportionality constant. So it's a constant value. To evaluate the proportionality constant K, we need to have one measurement of the solubility of a gas at a known pressure and temperature. So we can determine the K, which is a constant. This K can be defined at a known pressure and temperature. For example, the aqueous solubility of nitrogen gas at 0 Celsius degree and 1 atmosphere, so 0 Celsius degree, and pressure is 1 atm atmosphere, is about 23.4 milliliter per liter. So the Henry's law constant, K, can be calculated, these values, by dividing these values to each other. So this C value and then the pressure, partial pressure is known, and we can calculate this proportionality constant according to this. So let's suppose we want to increase the solubility of nitrogen to a value of 100 milliliter per liter. So this equation, the above equation in the pink area, suggests that to do so, we must increase the pressure of the nitrogen above the solution. So if you look at that, the pressure amount can be calculated according to this if we want to increase the solubility of nitrogen. So we have a figure on the right side, as you see. This figure says us the concentration of dissolved gas is proportional to the pressure of the gas above the solution. And then, as you see, there are increasing weights on the circular piston, and it's how the pressure affects this solubility. These weights are affecting some pressure there, and of course, the solubility affected from it. So as a summary of this slide, we can say that the pressure affects the solubility, it increases, and the temperature says about the temperature. Conversely, we say that the solubility of gas decreases with a decrease in pressure, and increase in temperature decreases the solubility of a gas in a liquid. As a summary, we can say that. Let's go on. About the temperature and pressure, we can say that in the mixture of gases, each constituent gas has a partial pressure, which is a notational pressure at that constituent gas if it's alone occupied by the entire volume of its original mixture at the same temperature. So the total pressure of an ideal gas mixture is the sum of the partial pressure of gases in this mixture. We can say that. So if this is actually another law describes the partial pressures of the gas. This is Dalton's law. So the partial pressure of a gas is a measure of thermodynamic activity of a gas of the gas molecules, and gases dissolve, diffuse, and react according to their partial pressures, but not according to their concentration in gas mixtures or liquids. So we can say the general property of gases is also true in chemical reactions of gases in biology, of course. For example, the necessary amount of oxygen for human respiration and then the amount of that is toxic is set by partial pressure of oxygen alone. So this is true across very wide range of different concentration of oxygen present in various inhaled breathed gases or dissolved in blood. So consequently, mixture ratios like that of breathable 20% of oxygen and 80% nitrogen are determined by the volume instead of by weight or mass, we can say. So the partial pressure of the oxygen and carbon dioxide are very important parameters in test of arterial blood gases, yes. So that's like the pressures, these pressures can also be measured, for example, cerebrospinal fluid. So because of this, these partial and temperature effects are so important for us. And we said that Henry's law described the behavior of gases when they come into contact with a liquid such as blood. And the concentration of a gas in a liquid is directly proportional to the solubility and partial pressure of that gas. And the greater partial pressure of the gas, the greater number of molecules that dissolve in the liquid. So for the blood, if we talk about the concentration of a gas in a liquid is also dependent on the solubility of gas in the liquid. For example, although nitrogen is present in the atmosphere, very, very little nitrogen dissolves in the blood because the solubility of nitrogen in blood is very low. And maybe this is one important detail about that. Yes, so we know the effect of temperature from our first slide. So on all conclusive generation about the effect of temperature and on the solubilities of gases in solvent is not possible. It is certainly true, though, that the solubilities of most gases in water decreases with an increase of temperature. So look at the figure, please. You can see the solubilities of some gases like helium, nitrogen, carbon monoxide. So you know, it's toxic. Carbon monoxide is toxic, and it has a middle solubility if you compare with oxygen, as you see, you can see their solubility values that. So effect of the temperature on solubilities of gases about dissolving air. So as you see on the right figure, we have dissolved air there. When you heat the water, even at the temperature well below the boiling point, it's released. So dissolved air is released when you heat the water. You can see them as bubbles, as you see on the right figure. So we can say, according to the left figure, left graph, the solubilities or the facts about the solubility differences of these gases can be explained why many types of fish can survive only in cold water. So there is not enough dissolved air or oxygen in warm water to sustain them. So this fact about the temperature effect for solubility of gases, and as you know, according to their proportionality constant, the gases have their own solubility values. Because of this, in our blood, it changes. So the composition of air in the atmosphere and in the alveoli differs. In both cases, the relative concentration of gases is nitrogen bigger than oxygen. So it's bigger than water vapor, and then it's bigger than the carbon dioxide relative concentration. So the amount of water vapor present in alveolar air is greater than in the atmospheric air, as you see in table 2. So recall that the respiratory system works to humidify incoming air. You know that we need this humidifying. So thereby causing the air present in the alveoli to have a greater amount of water vapor than the atmospheric air. So in addition, alveolar air contains a greater amount of carbon dioxide and less oxygen than the atmospheric air. So this is no surprise, as gas exchange removes oxygen and adds carbon dioxide to alveolar air. Both deep and forced breathing cause the alveolar air composition to be changed more rapidly than during quiet breathing. So as a result, we can say the partial pressure of oxygen and carbon dioxide change and affecting the diffusion process that moves these materials across the membrane. So this will cause oxygen to enter and carbon dioxide to leave the blood more quickly. Yes, these biophysical rules also effective on this. So yes, these are the details about these tables, we can say. So ventilation and perfusion. Look at that, please. We have ventilation without perfusion on the figure. We have diffusion abnormality on the figure. Also, we have perfusion without ventilation. So hyperventilation, normal ventilation, how it goes in the system. You can see on the right figure. Let's talk about this. So two important aspects of gas change in the lung are ventilation and perfusion. Ventilation is the movement of air into and out of the lungs. Perfusion is flow of blood in the pulmonary capillaries. So for gas exchange to be efficient, the volumes involved in ventilation and perfusion should be compatible. However, factors such as regional gravity, effects on blood, or blocked alveolar ducts or disease can cause ventilation and perfusion to be imbalance. So the partial pressure of oxygen in the alveolar air is about 104 millimeter mercury. And then, whereas the partial pressure of oxygenated pulmonary venous blood is about 100 millimeter mercury. So when ventilation is not effective, when ventilation is effective, when ventilation is sufficient, oxygen enters the alveoli at a high rate, and the partial pressure of oxygen in the alveoli remains high as a result of this. So, of course, if there are some diffusion abnormalities, there will be changes in this. There will be some changes in this value. So, in contrast, when ventilation is insufficient, the partial pressure of oxygen in the alveoli will what? It will, of course, drop. Without the large difference in partial pressure between the alveoli and the blood, the oxygen does not diffuse effectively across the respiratory membrane. So the body has mechanism that counteract this problem. We have some mechanism. So in cases when the ventilation is not sufficient for alveolus, the body redirects blood flow to alveoli that are receiving sufficient ventilation. So this is achieved by constricting the pulmonary arterioles that serves the dysfunctional alveolus. So we will have what? Redirection of blood to enter alveoli that have sufficient ventilation. So at the same time, the pulmonary arteries that serve alveoli receiving sufficient ventilation vasodilate. So this actually brings in greater blood flow. So this mechanism is important, okay? We have a mechanism for what? For if the ventilation is insufficient, and this is what actually body redirects blood flow to alveoli that are receiving sufficient ventilation. Okay, ventilation is regulated by diameter of the airways, whereas the perfusion is regulated by the diameter of blood vessels. In our other course, we will also talk about these diameter differences also. So the diameter of bronchioles is sensitive to the partial pressure of carbon dioxide in the alveoli. So greater partial pressure of carbon dioxide in the alveoli causes the bronchioles to increase the diameter. So also decreased level of oxygen in the blood supply allows carbon dioxide to be exhaled from the body at a greater rate. So greater partial pressure of oxygen in the alveoli causes the pulmonary arterioles to dilate. So this increase what? This will increase the blood flow. Yes. One more time, I will take the attendance. So we have 34 students now. Okay, I download it again. Okay. Okay, thank you. So yes, we will look at now external and internal respiration. So external respiration actually means gas exchange across the respiratory membrane in the lungs. What about internal respiration? Gas exchange across the respiratory membrane in the metabolizing tissues. So you can see this external and internal respiration again. So the external respiration between environment and the lungs, and then internal respiration between the blood and the cell. This is the main difference and main definitions between these. 1 minute, please. Okay, let's look at now gas exchange in the body. So gas exchange occurs at two sites in the body. In the lungs, where the oxygen is picked up and the carbon dioxide is released at the respiratory membrane, we know that. At the tissues, where the oxygen is released and the carbon dioxide is picked up, and the external respiration is the exchange of gases with the external environment and occurs in the alveoli and lungs. So let's go on with the internal one, internal respiration. Is exchange of gases with the internal environment and occurs in tissues. So the actual exchange of gases occurs due to simple diffusion, and the energy is not required to move the oxygen or carbon dioxide across the membranes. So for the internal respiration, we can say that instead, these gases flow pressure gradient that allow them to diffuse. So the anatomy of lung maximizes the diffusion of gases, and the respiratory membrane is highly permeable to gases. So the respiratory and blood capillary membranes are very thin, and there is a large surface area through the lungs, we can say. So external respiration, exchange of gas with external environment, and occurs in the alveoli of lungs, and internal respiration is the exchange of gases with the internal environment and occurs in tissues. Please mute your microphones. So the actual exchange of gases occurs due to simple diffusion. So diffusion of the gases, energy is not required to move oxygen and carbon dioxide across membranes. So instead, these gas flow pressure gradients that allow them to diffuse. I repeated this part again for you, which is an important part for this course. So, yes, the anatomy of lung maximize the diffusion of gases. It has an anatomy like that in your other courses you will learn also. So as you see, it has some connective tissues, capillary bands, alveolar duct, alveolar sacs. So we have mucosal lining, mucous gland. These are all effective. Also alveoli, the veins are take their roles during that. So the respiratory membrane is highly permeable to gases, and respiratory and blood capillary membranes are very thin. And then there is a large surface area throughout the lungs. So the pulmonary artery carries deoxygenated blood into the lungs from the heart. So here it branches and eventually becomes the capillary network composed of pulmonary capillaries. So these pulmonary capillaries create the respiratory membrane with the alveoli. As the blood pumps through the capillary network, what will be there? Of course, gas exchange occurs. Although a small amount of oxygen is able to dissolve directly into the plasma from the alveoli, most of the oxygen is picked up by the erythrocytes. You know that these are red blood cells. And then it binds to a protein called hemoglobin. So this process is also described more detailed in our other courses. So oxygenated hemoglobin is red. It will cause the alveoli appearance of bright red oxygenated blood, so which returns to the heart through the pulmonary veins. So carbon dioxide is released in the opposite direction of oxygen from the blood to the alveoli, and some of the carbon dioxide is returned on hemoglobin, but can also be dissolved in plasma, or it is present as a converted form. It is also explained in greater detail in your other courses. So external respiration occurs as a function of partial pressure. We know that. I want to remind you that this again. So as a function of partial pressure difference in oxygen and carbon dioxide between the alveoli and the blood pulmonary capillaries. So let's go on the details of external respiration. So although the solubility of oxygen in blood is not high, there is a drastic difference in the partial pressure of oxygen in the alveoli versus in the blood of the pulmonary capillaries. These differences about 64 millimeter mercury. So the partial pressure of oxygen in the alveoli is about 104 millimeter mercury. I said that in our previous slides. So whereas its partial pressure in the blood of capillary is about 40 millimeter mercury because of this difference, because of the difference in the pulmonary capillaries. So this large difference in partial pressure creates a very strong pressure gradient that causes oxygen to rapidly cross the respiratory membrane from the alveoli into the blood. So this difference is important, okay? So this difference will help us. This large difference will help us obtaining a very strong pressure gradient. And this pressure difference gradient, will cause oxygen to rapidly cross the respiratory membrane from the alveoli into the blood. So you know that. Let's look at the details again. The external respiration occurs as a function of partial pressure differences in oxygen and carbon dioxide between the alveoli and the blood pulmonary capillaries. I told you the details and the pressure differences between these. The solubility of oxygen in blood is not high, around 0.3 milliliter per deciliter of blood. Please mute your microphones. So most of the most of this transported via hemoglobin. As we have last 10 minutes. So for carbon dioxide, there are three possible ways of transport. You can see these ways on the figure. So as you see, dissolving in plasma, so carbonic anhydrous way, and then the by using the hemoglobin on the figure, you can see their steps. So in external respiration, oxygen diffuses across the respiratory membrane from the alveolus to the capillary, and then the carbon dioxide diffuses out of the capillary into alveolus. You can see this also in our figure. So, okay, we told about the difference. I said that it's important. The large difference in partial pressure, oxygen creates a very strong pressure gradient that causes oxygen to rapidly cross the respiratory membrane. I said that this is important. And then the carbon dioxide partial pressure difference between the capillary and alveoli is less than that oxygen, about 5 millimeter mercury. So not a large gradient created here. So however, the solubility of carbon dioxide is much greater than that of oxygen by factors about depending in both blood and the alveolar fluid. So as a result, we can say the relative concentration of oxygen and carbon dioxide that diffuse across the respiratory membrane is similar. So internal respiration is gas exchange that occurs at level of body tissues, as you see in the figure. And then the similar to external respiration, internal respiration also occurs as a simple diffusion due to parallel pressure gradient. We have again a gradient. So the partial pressure gradients are opposite of those pressure of those present at the respiratory membrane. The partial pressure oxygen in tissues is low. It's about 40 millimeter mercury because oxygen is continuously used for cellular respiration, as you know. In contrast, the partial pressure of oxygen in the blood is about 100 millimeter mercury, and this will create a pressure gradient. This causes oxygen to dissociate from hemoglobin, diffuse out of blood, and cross the intestinal space and enter in the tissues. So hemoglobin that has little oxygen bound to it loses much of its brightness. So that blood returning to the heart is more burgundy in color, if we talk about the color here. Okay, I told you everything about this slide. Yes, the partial pressure of oxygen in tissues is low. It's about 4 millimeter mercury. Yes, I told you also these details. Okay, so returning to heart, I said that. I told you there about the color. So by the time blood returns to heart, the partial pressure of oxygen has returned about 40 millimeter mercury, and the partial pressure of carbon dioxide has returned to about 35 millimeter mercury. So the blood is then pumped back to the lungs to be oxygenated once again during the external respiration. These are the steps. These are the important details for external and internal respiration. Actually, all of the things that this course are so important. This is the previous part of our other course. One more time, I will take the attendance. So I will take it as a screenshot. Okay. Yes, we have 4 minutes. I have some questions here. Okay, so try to solve them after the course. Try to solve it, please. If you have a problem solving these, I think when you study the presentation after the course, if you read it one more time, I think you can solve them easily. But if you can't, I can also help you, of course. In our group, we can talk about this. If you have any unclear points, I can help you, yes, let's finish this course today, and not today, sorry. After this, as you know, we have another course.